mind, was published in the case of atoms by Aarhus and others in 2010. And they have in their paper this figure here, where you have the red curve is the vector potential, and the black curve is the electric field. Let's look at this part here, where ionization from this instant of time and from this instant of time will give the same final vector potential. This is what Buxbaum talked about yesterday. We have two events in such a in this part of the cycle, in this so-called, there's another word that is often used in this so-called simple man model. You say that the final momentum of an electron ionized at time t I, for example, is obtained by the integral over the electric field like this. So you just neglect everything else. And what is this? This is nothing else but minus the vector potential. That means that these two values here of the vector potential contribute to the same momentum. They should be added coherently. And what you see here from this one here is that you have things that happen within the same cycle. So you have two contributions within each cycle. They are called intracycle, and contributions between different cycles are called intercycle. And this we did, now I think I want to show you that also. Why not? So here. So this is now from Lum's thesis. It's just to give you, I don't want to go through all these equations, but please focus over here. We're considering some matrix element, and we were having these phases here from the intracycle contributions, and we make to do this, to do the calculation which is necessary to make the interpretation, we need to define the average phase and the phase difference. And when you do that, you can write the probability, which is this sum of all those saddle points, and you can introduce those two things, namely the average phase and the phase difference, and then you can separate out a contribution coming from the phase difference, which will be intra-cycle things, and then the rest, which will be intercycle things. So, and this thesis will be online when he will submit in the end of this month. So after that, you can find it on the internet. So this, I hope at least somehow I gave you a feeling about how you can do this sum here, leading to basically an intra and an intra-cycle contribution. And this is now the result here. Here you see the full SFA at 400 nanometers, 800 and 1600 nanometers. And what you see here is kind of, you find some of the features which were in the TDSE calculations, right? And then I have plotted here separately the intra and intercycle interference effects. So this is one, and clearly you see here the intracycle one, you get these energy conserving diagonals, and the intracycle things, you see those things that look cross-diagonal and maybe at odds with the energy conservation. But it's an interference effect, and it's a nice challenge. Maybe you could try to think, I didn't discuss this with Brett, but maybe one could think about how to interpret this in terms of this carrying the phase picture. In any case, so these are the, so now we have covered this one here and this one here, and in fact this one here can also have, and this is what I show you here in the next view graph. What I have, so here you see now in this case, the energy of the electron is kind of very confined, and then you have some broad distribution over nuclear energies. How to understand that? Well, this is now showing that you can have just, so the only thing I did here was that I decreased, this is also 800 nanometers, so what I did was that I decreased the intensity a little bit. So at higher intensity, I got this result here, and now I decrease the intensity a little bit, and then suddenly I get this result. So why is this? So this is now more difficult, because to understand this, you need to look much more carefully into the dynamics. I don't think it makes much sense here to go into the dynamics in detail, but I can mention that in order to explain this and this fact that the electron seems to be discretized in energy is because at lower intensity we cannot readily ionize from here. We need to dissociate a little bit before we can ionize. And where we can do the ionization, we have in fact pretty much parallel curves. This means that that it doesn't depend on the internuclear distance and not on the nuclear energy. And that's why it suddenly looks like this. So maybe some conclusions at this point. At low frequency, we have talked in my lecture here about tunneling, and we have talked about the joint Indy spectra and intracycle interference. I should mention that this, I mean, this was predicted in atoms, but it's not really been very clearly observed. But it's clear that if I could convince someone to do such an experiment in a molecule, there should be extremely clear signatures of this effect. So now, there are many other things that you will meet in the literature when you look at strong field dissociation, so you will see all these terms here. I cannot possibly cover that, but there's a lot of different physical processes going on. Rather now, in the last part of this lecture, I'd like to take you into a kind of regime of the future a little bit, because new technology actually means that we can produce femtosecond pulses with intensities that are exceeding the atomic unit of intensity, and with photon energies above the ionization threshold. So this is a new regime, and how does breakup occur in this new regime? So that's what we wanted to ask about. So what is the characteristic breakup in that regime? So let's start. Again, I showed you this equation already. It's the same equation we solved. And there are some observations. Observation number one is that stabilization occurs. What is stabilization? Well, here what you see here is that this is the probability for ionization as function of the field strength, amplitude, so amplitude also, and for a fixed frequency in atomic units. And stabilization is this effect that you have a non-monotonic behavior of the ionization probability as function of field strength. Of course, you would assume that the more intense you make your pulse, the more ionization you will get. That's kind of the dimension of distribution I expected. But since, I think, the 80s, it has been known that you can have something called stabilization. And stabilization simply means that you have this decrease in the ionization yield as function. So this is one thing you can have. The new thing here, compared to what was known, is that this is now done in a molecule. So you can have stabilization in a molecule, including nuclear motion. What happens then here when you have stabilized the ionization? Then the other new observation is that you can then have a big dissociation probability. And this is what is shown here. Again, dissociation probability versus field strength. And you see at low field strength it's unlikely because you ionize, but then as you increase the field strength, you can have a lot of ionization. Dissociation. So how can that be? So this all came out of our TPSE calculations. And then the job, when you do theory based on the TPSE, the job is like doing an experiment. Then we still have to do some other theory to make an interpretation of what came out from the TPSE. at least in some cases. And to do that, we need to go through this slide, which I also prepared yesterday evening. It's because this is better done in another frame, which is a non-inertial frame, which is called the Madsen frame. Then I thought it would be good just to make sure that you know how to shift between different points of view. You have the length gauge, where the electric field interaction is field times r. You have the velocity gauge, where the electric field interaction is a dot p. But you also have other things. And all these things can be generated using these two lines here. If I have a time-dependent Schrödinger equation looking like this, I can define another one, psi prime, which is nothing else but some unitary transformation, a unitary operator times psi. So in this slide here, u is not the time evolution operator, just the unitary operator. If now I isolate psi from this equation and plug it into the original time-dependent Schrödinger equation, I get a new equation. This is left as an exercise for this new psi prime, where the Hamiltonian is transformed like this. So you have a unitary transformed thing here, and then you have this term here, which involves time derivative. In some courses in quantum mechanics, students learn about this. In some, they don't. How many have seen this before? Okay, it was worthwhile to show it. And what is the point? The point is that now, typically, we have this equation here, I dt psi velocity gauge representation, where you have this interaction term. And then, in fact, you can get this one here, called Kramers-Henneberger, by using this rule up here and this operator. E to the minus I alpha log p, where alpha is the integral of the vector potential. And then to evaluate this explicitly, you see that you get like, for example, in here you would get e to the minus I alpha p, p of r, and then the Madsen conjugate of this operator. So you need somehow to be able to do some commutators of some operators. And there's another thing you have to look up in your quantum mechanics book, what's the Baker-Hauser operators. I wrote it down here for two Madsen operators, D and B. So with these tools, you can basically get from this equation to this equation. And except that I apparently miss a parenthesis here, it's correct, and it's the expression for the interaction in the Kramers-Henneberger frame. And you see here, suddenly the interaction with the external field somehow disappeared. Explicitly kind of disappeared as a term, as a direct additive term in Hamiltonian, but it came in here in the potential. So what it means is that, for example, if you had the Coulomb potential, we use the equation there, then it would be minus 1 over r plus alpha of t. Right? So if I had the Coulomb potential looking like this, say without any external field, then at some instant of time in this field, I would have shifted the origin. Right? So maybe at some instant of time, I would have the origin here, and so at other instant of time, I would have the origin here, and so on and so forth. And this is what we do. So it's instructive to transform the TDSE into the Kramers-Henneberger frame. So the point here was that it's not because we needed to do that for this our small problem. It's because it's good to know how to do it, and you can often benefit from this picture also in your analysis of any of the software. Here is it looks a little bit more complicated now with some factor beta here that depends on the masses because we have the molecule. And now we have this potential here. And then the final step is to say that, okay, this potential here, which is the potential of time, I can decompose into Fourier components. Right? And if alpha here is very big, this quiver motion. So maybe I wrote it here. So the dimension of this here is momentum. So if I integrate momentum, I get physically displacement. So if alpha here is very big, it goes like this. And then if it goes very, very fast, then of course the n equals 0 term here in the potential dominates, right? And this is this potential here. This is the dominating term in this Fourier decomposition. So this here is the dominating term. It's just the time averaged Kronos-Henneberg potential. And therefore you're led to a structure equation. So you're led to a structure equation involving kinetic energy of the nuclear and the Hamiltonian of the electronic part with this time averaged potential. And doing this, we can obtain new Dress-von-Oppenheim curves. And this is what I show here. So this is also something you will meet a lot when you discuss molecules. Maybe not Dress-Kronos-Henneberg potential curves, but Dress potential curves. And here's one example of such Dress potential curves. And in this particular example, I have this curve initially, and then I have now, let's say, this one here finally. And the dynamics at play here, the dynamics that explains that I could get so much dissociation is actually explained in this view graph. Because initially, I have this system here, I increase my field strength, I get a Dress-von-Oppenheim curve, I increase the field strength even more, I get this one up here. It's above the limit of dissociation. And the way I manipulate the laser in this particular case is such that this state can more or less follow adiabatically up. But once it's up, the time scale of the, you see the energy levels here are decreased compared to the energy levels here because the well is wider. The nucleus now moves slower. It doesn't have time to come back again when the field is switched off. So kind of simplistically, it follows up adiabatically, but then when it's up there, it's moving too slow to follow down again. And then it's suddenly trapped there, and this field is gone and moves out. And this leads to dissociation. And this picture you can use in many cases like this. So you can have it here. In this case, the pulse is very short. It's so short that the nuclear wave function doesn't have time to follow. In this case, this is the case we just discussed. In this case, the pulse is very, very long. So in this case, the nuclear wave length has time to follow up and down. And this you can do for cases when you have a field strength or corresponding to a given amplitude, which is proportional to the field strength. You can have both above the threshold for dissociation, but you can also have it below. So in this sense, this can be controlled. And it is, in fact, this is kind of the model. And this model comes out from the TDSE calculations, where we show, again, field strengths on the x-axis, and then here we show vibration quantum numbers for the bound state and the nuclear kinetic energy for the continuum states, and we do this for different cycles. Very long cycle, very short cycle. For the same, and if we just remember my picture here from before, I said if the pulse is very long, this wave packet will follow up adiabatically and adiabatically down. This is in fact what you see, because after the pulse, we only have population in the vibration ground state for this very long pulse. When the pulse is shorter, we have some vibration excitation. In this picture, it's like it goes up, but it can't really follow all the way down. And over here, if the pulse is very short, we just have a little bit of sudden excitation of the vibration states. And this case here is the case when we can have a lot of dissociation also. So to put this in a more general framework, so it's good sometimes to think about Dress potential energy curves. In this case, in the Kronos-Henneberg frame, it could be other kind of Dress potential energy curves, and then try to make an interpretation in terms of that. And another central topic here is this issue about timescales of the nuclear motion in this case. What is the timescale of the nuclear motion compared to the timescale of the way you change your field? So the field could be sudden from the point of view of the nuclei, but not sudden from the point of view of the electron. Okay, so what we have found here is that stabilization against ionization occurs. Dissociation may completely dominate over ionization in this machine. And the vibration distribution, dissociation yield, and nuclear kinetic energy release may be controlled by pulse parameters. Because if the field is not sufficiently intense, I can trap the population in some vibrationally excited states. Okay, so at this point, we have seen a lot of examples of electronuclear correlation. What we have not discussed, because in fact I only discussed H2+, is how do electron-electron correlation affect strong field and attosecond physics. For example, what is the validity of those models we often use? What is the validity of the single active electron model, the two-step model, the three-step model, and so on? So this is going to be the topic of my last lecture tomorrow. So now we have learned a lot from single active electron models. We know something about electron-nuclear correlation. How should we add electron-electron correlation, and what will we learn from that? That's somehow the topic for tomorrow. I think that's it, because I skipped this. You have had enough, I think. Yes. Thank you very much.
Thank you very much.
Could you just clarify this stabilization? When the stabilization goes down, that seems to be exactly when the dissociation increases.
Yeah.
So it's stabilization in an unusual sense, because the target is changing.
Yes, so just to show how I understand the question. So this here was the first figure showing ionization probability as function of field strength. It goes up and stabilizes. And you see this starts to stabilize around here, you would say, a peak here and then stabilize. And then we go to this one, maybe stabilize here.
Yes.
and then this one goes up, as you point out. It's true that to see this effect, to see this huge increase in dissociation, of course you cannot afford that the system ionizes. And that's your point. And therefore it's also clear that it has to be under some kind of exotic conditions, because in any normal system, I guess you would have more resonant ionization process than you would say that this highly non-resonant dissociation process. But one should not be led by that kind of standard. I mean, if you think in terms of few photon process, if you stack one photon on top of that curve, you say clearly it ionizes. This is the resonant one, and the dissociation is very non-resonant. But the central point here is that then to understand this mechanism, we actually need to go into this Kamasenan frame and think in terms of these stress monopole. And then you would say, what happens then if I do not have a single electron system? And this is a very interesting question that requires more work for the future.
There are still two ways of interpreting this. You could say, well, you have the molecule, and you can ionize it, but this stabilizes, and so you have a certain fraction of your target that's not ionized. But you would say another fraction is dissociated, so two separate things. But if you think of a single molecule, then it becomes more difficult how you define stabilization if it's dissociated.
Well, I mean, the definition here is that dissociation is when the final state is a proton and a hydrogen. And ionization in this one would be two protons. Yeah. And.
So let me try this. So what if I think of Renner and Anderson
stabilization is I have an electron oscillating. Sort of, I like to think of it like that. Oscillating off to the side, and of course it's best bound if its extrema is near the nucleus. So by adiabatically moving the populace, and by letting the system evolve adiabatically, are you moving the electron essentially out of its bonding position between the atoms, pushing it off to the side where it's wiggling like that, and then you let it free, the electron is no longer. Turn on the field, the electron is out where it was binding the wall. Could it be fit in this physical way? Not sure it's very articulate.
No, actually, I cannot. Maybe, I don't know. It's certainly what you're saying is different from what I give here.
Well, I'm not sure it's different, that's why.
Yeah, well, this is,
You said you adiabatically.
yeah, so this here is the curve for a given field strength. Then I increase the field strength, then I have this curve. Then I increase the field strength even more, then I have this curve. And this is actually the vibrational ground state density in that state.
So it's adiabatically changed.
So this is how it's changed. But of course, this curve doesn't say anything about how the electron moves in itself, because this is the solution that comes out from solving the electronic problem.
I wonder if that's what really happens.
Yeah, I mean, it is in that sense that to the extent that this, what you say, is of course reflected in this continuum. Yeah, and it seems to me that what you say has more to it than what I could answer now. So let's discuss that.
Yeah.
Since you're solving the TESE here, I assume that it's the 1D H2 plus.
Yeah.
Well, we also know that stabilization, all of that is exaggerated in 1D compared to 3D. So how do you expect this to survive when you go to a real 3D problem?
Yeah, this was this we addressed a lot in this, this one. In fact, there's and this was we had very constructive comments from a referee, or actually from two referees, and they were both constructive. And they asked about this, and they asked about what if now I have a multi-electron molecule. And those issues are discussed in the end about it. And the brief answer is that you also have this effect in 3D, and you also have, some people have in fact done this type of calculations for 3D molecules and find the same trend. This was done in the 90s by a French group and also from Gabriela and collaborators. So we expect that this could occur. So for this mechanism to run, you need some degree of stabilization, and then you also need, and this is what we're investigating now. But it's clear that it's not. If now you have, so can I answer quickly? So now just to make clear, here's the ionization potential. And this now here is some simple picture of some atomic or molecular system with more than one electron. So this is a neat field photon. If these guys here are stabilized, it maybe requires that the photon energy is like this. So now it was a bad one. Down here I have some other states. And this may be, the valence may be stabilized because the binding energy is less than the photon. But now you can see that maybe in this particular case, I could go to the continuum with a 3-photon process. So if it's not good for us if the valence is stabilized and I have that's bad wording. It's very interesting to think about what this then means. Right? We can have a competing multi-photon ionization channel from an inner shell occurring simultaneously with some dynamics of the outer one. And this physics here is something we have to begin to take serious because this was the motivation for this work, because these pulses are being produced now. So all this stabilization was discussed a lot some years ago, but I think now we have to look at that. We have to look at this pulse regime.